We're going to solve exponential equations. The first equation, I'm going to give you an example, is to solve the equation 2 to the 3x plus 1 is 32. This is an easier problem because it turns out 32, if I get the prime factorizations, is just 2 to the 5th. So I'm really asking what value, because I'm solving for x, of x will make 2 to the 3x plus 1 power equal to 2 to the 5th. In order for 2 to this power to equal 2 to this power, those two powers must be identical. So all we need to do is solve 3x plus 1 equals 5. And then because those two, it's the same base to the same power, they must be identical powers. Working this through, I subtract 1 and I get 3x is 4. Divide both sides by 3 and I get that the value for the exponent value for x is 4/3. But now we'll look at another problem. Suppose I said instead of solving for x 2 to the 3x plus 1, what if I said 2 to the x is 19? What's different about this problem is 19 is not a power of 2 that we readily look at. So this is going to involve using one of our properties of logarithms that's going to actually release the x from the exponent. In this problem, what we're going to do is I'm going to take the common log of both sides. So I'm going to say the log of 2 to the x must be the log of 19. I just took the common log of both sides. If both of these sides are equal, their logarithms must also be equal. By the property of logs, the x goes in front, and this becomes x times the log of 2 equals the log of 19. Now it's x times log 2 is actually a number, so log 19 is also a number. If I want to get x by itself, I'm just going to divide by that number. So I just divide both sides by log 2, and that gives me that x is log 19, the common log of 19, divided by the log of 2. Now this is what we call an exact answer. I call this an exact answer. But on our calculator, we have to get an approximate answer. So I'll do this to 4 decimals. And this is approximately, I take the log of 19, and then I divide it by the log of 2, and I get the answer is approximately 4.2479, and I'll round that to 3. So what this is telling us, that seems correct. If we go back here to the equation, this is saying 2 to the approximate 4.24793. The numbers actually go on forever, equals 19. And that seems appropriate because 2 to the 4th is 16 and 2 to the 5th being 32. So that becomes our value for x. So the important part, we started with this exponential, and the important step was we took or take the log of both sides. That's how we're going to solve these. And once we do that, then we use our property of logarithms to go on further. Working another problem, so for example, suppose I say solve for x, and I say 2 to the 3x plus 1 is 38. First step is we look and we see 38 is not a power of 2. So that means we're going to have to work this with logarithms. So we're going to take the log of both sides. Okay? Take the log of both sides. The reason we do this, we now have this exponent, and this can go in front. So I have parentheses 3x plus 1 log 2. That whole exponent went in front and was multiplied times log 2 equals log 38. Now we're going to divide both sides by log 2. And that gives us 3x plus 1 is log 38 divided by log 2. This is going to be a number. We're trying to isolate x, so we'll subtract 1. This log 38 over log 2 is a number, a decimal. We'll worry about that later. So we get 3x is log 38 divided by log 2 minus 1. To solve for x, I would divide by 3, or I can think of it as multiplying by 1/3. So I'm multiplying both parts here by 1/3. This gives me that x is, I can write this log 38 and 3 times log 2 minus 1 times a third minus a third. This is the exact answer. And now the next thing we can do is use our calculator to get an approximate answer. And I'll do that with 4 decimal places. So this is approximately 1.4160. And I just rounded this to 4 decimal places.